Have you ever asked yourself where the boundaries of our universe are? How far exactly it extends? My guess is you would not have come up with a satisfactory answer even if you spent hours on end trying to figure it out. No wonder, as the universe is like the horizon. You take one step forward and it glides 2 steps further away from you. In spite of this disappointing fact, a great number of really fascinating discoveries in space exploration have been made in science. And now I'll tell you about a few of them. We will set out on a journey to the boundaries of our Milky Way, reach the limits of the observable universe, take a look at a pulsar, the TRAPPIST-1 system, a magnetar, the most massive black hole, and we'll speculate about why we still haven't come across any intelligent life forms in our pursuit of exploring the universe. An exciting journey is up ahead. Let's get started. Cosmo, the first in outer space. Galaxy is a common name for a system of stars, clusters, interstellar gas, dust, dark matter and planets which all are bound together by one gravitational energy. All objects in a galaxy are in motion with respect to the general center of its mass. As a rule, these are really remote astronomical objects, with the distances to them measured in megaparsecs. We can make out only several of them with the naked eye. The Andromeda Galaxy, seen in the northern hemisphere, the Large and Small Magellanic Clouds, seen in the southern hemisphere, and the M33 Galaxy in the Triangulum constellation, seen from the northern hemisphere as well. The exact number of galaxies in the observable part of the universe isn't known, but their number may well reach 2 trillion. Only in the 20th century was it made possible to observe some of them. By the early 1990s, not more than 30 galaxies were registered where stars were visible and which were part of the local group, that is, the cluster of galaxies forming one large hole known as the Virgo supercluster. After the launch of the Hubble telescope in April 1990, however, the inflow of information about new galaxies soared dramatically. Today, they are subdivided into several general classes. The first class is satellite or companion galaxies, which are objects orbiting around a larger galaxy due to the gravity of the latter. The second class is spiral galaxies, which are peculiar for the central bulge cocooned in a disk. And the third class is irregular galaxies, typically unsuited to either of the proposed categories. As a rule, they are chaotic formations with neither a clear nucleus nor spiral arms. Lenticular or SO galaxies, elliptical galaxies and barred spiral galaxies like our own Milky Way fall into this category too. The approximate diameter of each of them ranges from 5 to 250 kiloparsecs or 16 to 800,000 light-years. Just to compare, the diameter of the Milky Way is 30 kiloparsecs, that is 100,000 light-years. The largest galaxy known today is called IC 1101 and it boasts a diameter of over 6 million light-years. The principal problem in studying the structure of a galaxy is the mystery of the dark matter. Today, the dark matter is believed to account for up to 90% of the overall mass of a given galaxy. Alternatively, another galaxy may be completely devoid of it. But which of these objects can be defined as the nearest to us? Many would argue that it's the Andromeda Galaxy that is the closest, which is located 2.52 million light-years away. However, this is the closest object among the largest spiral galaxies. As for the closest galaxy, a hypothetical Canis Major dwarf galaxy should be named. This astronomical object belongs to the local group as well. The galaxy contains a comparatively high percentage of red giant stars and presumably a billion regular stars. It is classified as an irregular galaxy and is officially considered our nearest neighbor. The galaxy is located 25,000 light-years away from the Solar System and 42,000 light-years from the center of the Milky Way. This object was discovered in November 2003 by an international team of astronomers. In spite of its close location to the Earth, the galaxy wasn't easy to spot because it is located beyond the plane of the Milky Way in the area with stellar, gas and dust overdensity. Our second closest neighbor is the Sagittarius Dwarf Elliptical Galaxy, which used to be considered the first one as well. It is a satellite galaxy with a clearly defined elliptical structure with its orbit passing over the Milky Way. The object contains 4 globular stellar clusters, with the first of them discovered in 1994, which led to the discovery of the galaxy itself. Its diameter makes up about 10,000 light-years. It is about 70,000 light-years away from the Earth and 50,000 light-years away from the core of the Milky Way. It is thanks to this galaxy that the Milky Way may have obtained its arm structure. This conclusion is based on numerical modeling. It was arrived at by researchers from the University of Pittsburgh. According to their version, the arms of our galaxy may have been obtained as a result of a collision with the Sagittarius Dwarf Elliptical Galaxy. This object is currently in the process of merging with the Milky Way. It should be noted that it has passed through the plane of our galaxy several times. The last time took place about 150 million years ago, which agrees with the data received by the Gaia telescope. When speaking about our nearest neighbors, one can't but mention the Large and the Small Magellanic Clouds, 2 dwarf galaxies and satellites of the Milky Way. The Large Magellanic Cloud is 163,000 light-years away from us. That is a distance almost 1.5 times bigger than our galaxy. The Large Magellanic Cloud finds itself in the area between the Dorado and Mensa constellations in the southern hemisphere, which is the reason why it is unlikely to be seen from most of Eurasia. The galaxy is approximately 10 times smaller than the Milky Way and contains approximately 30 billion stars. The mass of the Large Magellanic Cloud is about 300 times as small as that of our galaxy. However, it does not prevent it from holding the 4th place among all the local group galaxies in terms of its mass, beaten only by the Andromeda Galaxy, the Milky Way Galaxy and the Triangulum Galaxy. One of the best-known objects in this galaxy is WOH G64, a star considered to be one of the largest known to science. Its radius is 1,540 times that of the Sun. Hypothetically placed in the core of the Solar System, it would reach as far as the orbit of Saturn with its edges. The Milky Way and the Large Magellanic Cloud are expected to collide in approximately 2.4 billion years' time. Its neighbor, a Small Magellanic Cloud, should also be mentioned. It is a dwarf galaxy too, and is enveloped in neutral hydrogen. The small cloud is 60 kiloparsecs away from us. That is approximately 195,000 light-years. It is located in the Tucana constellation and has the appearance of a faint spot about 3 degrees in size. 1.5 billion stars are thought to be found in the Small Magellanic Cloud. However, they are not visible from most of Eurasia either. According to the data published in September 2014, the Milky Way is likely to swallow up this object as well in 4 billion years' time. To date, the number of satellite galaxies in the Milky Way equals 18, but the number of large systems closest to us reaches 115. This is hardly the full list of these objects, because new dwarf systems are discovered now from time to time not far from the Milky Way. Pinpointing and exploring objects like that is a rather arduous task. However, the search for nearest galaxies remains one of the chief objectives in astronomy today. Their discovery might give us insights into new planets similar to the Earth and might lead to the discovery of life forms in the nearest parts of the universe. The statement that there are boundaries to the universe is considered per se one of those great ideas which are able to dramatically change our world perception. Something similar took place back in 1543 when Nicholas Copernicus proved that the Earth wasn't located in the center of the cosmos. The following breakthrough took place in the 20th century when Edwin Hubble showed to the world that galaxies moved away from each other. This prompted the idea that the universe hasn't existed eternally and was formed as a result of a certain event, the Big Bang. Today we are certain that the dimensions of the world we live in are much larger than we are capable of imagining. The search for the answer to the question about its boundaries is going to lead to yet another scientific breakthrough. At the moment, scientists are able to talk only of the boundaries within which the objects are visible. This area is also called the observable universe. That is its part which is the absolute past in relation to the observer. The cosmic horizon is the boundary of the observable universe. The objects on the horizon become infinitely redshifted, that is, they constantly move further away. The number of galaxies within the observable universe is estimated at upwards of 500 billion, with this number increasing on a regular basis as the research equipment becomes more advanced. But how big is the observable area of the universe today? The distance to the remotest observable object equals approximately 14 billion parsecs in all directions. Thus, the observable universe is a sphere with a diameter of about 93 billion light-years and with the center inside the solar system. That is, it is centered on the observer. The area equals 350 quinvigintillion cubic meters. It should be mentioned that the light emitted by the furthermost observable objects has been traveling for 13.8 billion light-years before reaching us. However, the distance to those objects has significantly grown due to the never-ceasing expansion of the universe. This process is the result of there being matter and energy in space, filling space-time. While there is matter in space, there is gravitational force. Therefore, the universe either shrinks, affected by gravity, or expands, affected by dark matter. It is also worth noting that there isn't a single center for the universe's expansion, just like there isn't a space for the universe to expand into beyond its boundaries. This process takes place with the matter in space at any point, everywhere and at all times. We do not physically perceive this, as the force holding our atoms and molecules together does not allow us to burst under the influence of the space expansion. This may be compared to a baking loaf of bread, with the raisins for galaxies and similar formations and the dough for the space matter. According to estimates, the distance to the furthermost observable objects today equals approximately 14 gigaparsecs, or 46 billion light-years. The furthermost stellar system with respect to the Earth is a galaxy dubbed GN-Z11. Its light has been traveling to us for about 13.4 billion years, meaning that this object was formed less than 400 million years after the Big Bang. However, due to the constant expansion of the universe, today's distance to GN-Z11 is approximately 32 billion light-years. One may argue that the speed with which it recedes exceeds the speed of light, but it does not clash with the special theory of relativity, as it isn't the matter that is receding, but the space between the two objects is growing larger. This object is supposedly one of the very first galaxies and is likely to be the closest stellar cluster to the edge of the observable universe. If man were able to freely travel from one world to another, it is in that galaxy that we might find out about the genesis of our world in more detail. What we call the meta-galaxy is likely to have started to expand immediately on its birth. In theory, the boundaries of the meta-galaxy may well reach the cosmic singularity, That is, it may show us what the world had been like before the Big Bang, but in practice it is relic radiation that is the limit to the observable. It is this radiation that is emitted by the furthermost object in the universe to have been observed in contemporary science. This radiation poses something like a barrier for our vision. It came about approximately 380,000 years after the Big Bang. That is, at the time when the universe cooled off sufficiently for atoms to emerge. In plain English, it is similar to an image of space in its childhood, where it is depicted before the formation of the first stars. It is likely that the universe stretches infinitely beyond this barrier, and it is there that its hypothetical boundaries are to be found. The objects beyond this barrier are referred to in a number of ways: multiverse objects, parallel universe objects, to name but two. Science today is incapable of defining these bodies with any detail. However, assuming that the universe carries on expanding, we may conclude that the objects we are able to observe now are sooner or later going to disappear from our field of vision. If the accelerating expansion of the universe continues indefinitely, the galaxies beyond our supercluster are sooner or later going to recede beyond the horizon as a result, thus becoming invisible to us. Any form of communication beyond the boundaries of the observable universe will be rendered impossible, and any contact between the objects will be lost. The Earth, the Solar System, the Milky Way and our supercluster will be mutually observable, whereas the rest of the universe will recede in the distance. There may be hypothetical worlds beyond the regions observable to us. They originate as a result of phase transitions of physical vacuum. Alternatively, there may be objects forming out of irregularities of relic radiation located closest to the particle horizon. The question of multiverse objects remains a bone of contention among scientists, prompting an overwhelming number of pseudo-scientific guesses. Be it as it may, most researchers see eye to eye as to the infinity of our universe, although they interpret it in different ways. Some of them claim our world to be multidimensional, which makes our three-dimensional universe merely one of its layers. Others are inclined to believe in the theory of a multi-universe, with us as a minuscule fraction of an infinite multitude, whereas there may be a portal to other worlds beyond the observable area of the universe. Some space theories involve the existence of the so-called event horizon. According to this concept, we're never going to be able to look beyond the event horizon, because the speed at which photons travel away from us will be higher than the speed with which the observable universe expands. According to this theory, all the galaxies surrounding us are bound to recede beyond the event horizon. It will look like time stopped in them. We will observe them infinitely receding beyond the observable boundaries, but never quite disappearing from view. Be it as it may, contemporary science cannot provide a definite answer to this question, although the situation may change overnight once we have developed more advanced observation equipment. The universe might turn out to be a sort of sphere, and traveling over it might remind one of traveling on the spherical surface of our Earth. Considering the scale it reaches, however, this prospect appears impossible. In order to reach the edge of the observable universe, it would take man 46 billion years, even if we travel at the speed of light. By the time we reached this designated point, it would have moved the same distance away, and a similar journey would have to be embarked upon. It is likely that there aren't any large objects beyond the observable universe, and on peering there, we would see just a homogeneous cloud of helium, hydrogen, and a few other elements. However, we might probably never be able to discover the origins of our world, and might forever remain in the position of someone chasing the horizon. July 1967. A series of pulses was detected with the help of a radio telescope at Cambridge University by a postgraduate Jocelyn Bell. They emanated from a pulsar as yet unknown at the time, and the results of the observations were kept secret for several months. The object was initially designated LGM-1, which stood for Little Green Men. The name was given following the assumption that these perfectly regular pulses were not a natural phenomenon but signals of artificial origin, supposedly transmitted by an alien civilization. Besides, the team of scientists under Jocelyn Bell discovered 3 other sources of similar signals. The phenomenon took 7 years to investigate, and the thesis advisor of Jocelyn Bell's team was later awarded the Nobel Prize for studying this celestial body, which was subsequently dubbed PSR B1919+21. This pulsar was the first registered phenomenon of its kind. Its source was to be discovered several years later in the constellation Vulpecula, or Little Fox, 2,283 light-years from the Earth. Information about PSR B1919+21 was made public in February 1968, and by 1969 the number of detected pulses of this kind reached 27, and the term pulsar was coined as the official name for these objects. The first discovered source of this signal was the object dubbed PO943. It was spotted by Soviet astronomers in the Leo constellation. One of the most widespread assumptions at the time regarding this discovery was that all pulsars were in fact ultra-powerful radio beacons of extraterrestrial civilizations, and the pulsating signals remind one of a lighthouse twinkling in the night. However, it wasn't long before astronomers agreed that the regular signals were most likely emanated by neutron stars. Today, it is posited that these impulses originate as a result of a neutron star's spinning, and are in fact thin beams of radio waves. They are detected by the observer at precise regular intervals, which accounts for the pulsed appearance of this emission. Approximately 1,790 pulsars had been discovered by 2008. All of them were powerful sources of impulse radio emissions in space. As for the pulsars closest to us, they are located several dozen light-years away from the Sun. After pulsars were first detected, other pulsating sources of similar nature were registered by astronomers. They were described as powerful flares of regular intermittent X-ray emissions. Thus they got their name, X-ray pulsars. X-ray pulsars are also highly magnetized neutron stars, but unlike radio pulsars, which use their own rotational energy, X-ray pulsars are powered by accretion disks. An accretion disk is formed from material captured from the companion star, with the latter eventually becoming a white dwarf with all of its resources depleted. Thus, the mass and spin rate of X-ray pulsars gradually build up during the course of their revolution. As for radio pulsars, they on the contrary slow down as time goes by. For example, the average radio pulsar completes one rotation within the period from several seconds to several tenths of a second, with X-ray pulsars completing hundreds of rotations within the same time period. One of celestial bodies of this kind was discovered quite recently, and it is located rather close to our system. The object was dubbed J1023+0038, and its source caught astronomers' eye as recently as at the beginning of the 21st century. However, its pulses reached the Earth only in 2017. This was the first ever millisecond optical pulsar to be discovered. In essence, such celestial bodies are neutron stars as well. With a rotation period ranging from 1 to 10 milliseconds, the spin rate of these pulsars is several times that of regular pulsars. They form part of binary systems, and their spin rate increases to incredible speeds as the direct result of the pulsar pulling material from the gaseous disk produced by its companion star of a smaller mass. It should be noted that when a neutron star is in its active accretion phase, we see it as a source of X-rays. When the rate at which it pulls the material drops, bright pulsed radiation can be seen in the radio and gamma spectra. To date, a few more pulsars of this transitional kind are known to science, which fluctuate between the X-ray and radio spectra in a similar manner. However, it was the first ever transitional optical pulsar with a spin rate of this intensity discovered by scientists. The rotation period of J1023 plus 0038 is 1.69 milliseconds, which is 0.00169 of a second. The object itself is 4,500 light-years away from us. The mass of its companion star is 0.2 that of the Sun. It takes the pulsar 4.45 hours to orbit its companion star once. To date, the properties of J1023 plus 0038 have not been investigated in detail, although it is likely to be a not very massive neutron star. Although the object was initially considered to be a radio pulsar, in 2013 scientists noticed that its impulses regularly subsided and it was known to flare up in the X-ray spectrum. According to scientists, this phenomenon may be accounted for by the fact that the pulsar was at the moment in between the phases, which looks like the following. Radio emissions occur when material from the companion star is pulled to the pulsar, but star wind does not allow material to form an accretion disk. That is why the gas cannot heat up much and looks brighter in the radio spectrum. In the second phase, the stream of material from the companion of J1023 plus 0038 gets stronger and forms an accretion disk around the pulsar. The disk is in fact the source of observable X-ray emissions. It wasn't long before millisecond pulsating was detected in the optical band of J1023 plus 0038. As testified by earlier observations carried out with the help of the Swift X-ray telescope, the neutron star was surrounded by an accretion disk at the time. According to those in charge of the studies, the pulsar may have started to flare up in the optical band due to electrons in its magnetosphere when these electrons' speed was close to the speed of light. In the future, astrophysicists plan to conduct additional observations to study processes taking place within this binary system. And now to the object of the kind located furthest away from us that is known to science. It is NGC 5907X1, a celestial body which is also the brightest of all pulsars discovered by now. Spotted in 2017, this pulsar is an ultra-bright X-ray source. Shockingly, it releases as much energy in one rotation period as the Sun produces in 3.5 years. Earlier, astrophysicists believed these ultra-bright X-ray sources to be black holes. However, after the discovery of NGC 5907X1, it became known that they may turn out to be pulsars too. The object is located approximately 50 million light-years away from our Sun. As for its spin rate, it is variable. For example, in 2003, the rotation period of the pulsar was 1.43 seconds. Whereas in 2014 it dropped to 1.13 seconds. Just to compare, if our Earth were to be able to change its rotation speed in the same manner, a day on our planet would last just 19 hours. Modern astrophysical models cannot account for the intense luminosity of NGC 5907X1, although scientists believe it to have something to do with a powerful multipolar magnetic field that may be concealed within the pulsar. It will take even more complex studies to find out the reason for the emission of such staggering amounts of energy. Just a few decades ago, the phenomenon of a pulsar was beyond any explanation, and today science is able to differentiate between this phenomenon and any other in space. Our civilization strides forward, which leads us to believe that even this century may reveal a number of other phenomena unheard of in the past. The universe is like a giant canvas with quite a few blank areas. As our knowledge about space builds up, the pattern on the canvas gets altered too. With regularly applied changes, it may soon turn into a fully fledged map of our enormous universe, explored by man. This object is a single star with a planetary system, and there are at least 3 celestial bodies within the habitable zone. Now let's look at it in more detail. The distance between TRAPPIST-1 and our Sun is 39.5 light-years. The object was discovered in the period from 2016 to 2017. This single star is a red dwarf of spectral type M8V. As for its dimensions, it is only 12.1% of our Sun's radius. Just to compare, it isn't in fact much larger than Jupiter. The mass of TRAPPIST-1 is 27,000 times that of our Earth, but at the same time is 0.08 the mass of our Sun. With the average temperature reaching 2500 kelvins, its luminosity is 1900 times weaker in comparison with that of the main star of our system. The orbital period of TRAPPIST-1 is 3.3 days. As for its age, it is 7.5 billion years, which makes it almost 3 billion years older than the Sun. The distance between this star and us is diminishing, as it is slowly but surely drifting towards our system. This object aroused interest largely following the discovery of its planetary system back in 2016, whose 3 components were spotted by transit method with the help of an automated 0.6-meter telescope in the European Southern Observatory, or the ESO, in Chile. The planets were initially dubbed TRAPPIST-1b, TRAPPIST-1c, and TRAPPIST-1d. However, further investigations revealed that the presumed location of TRAPPIST-1d was described incorrectly. Following that, 4 more Earth-like objects were discovered by astronomers with the help of the Spitzer Space Telescope. These were dubbed TRAPPIST-E, F, G, and H. Thus, the total number of planets in the system reached 7, and on the 13th of April 2016, the parameters of these celestial objects were defined in more detail. All the 7 exoplanets are identical to our Earth in terms of their dimensions, with their radii ranging from 0.71 to 1.13 that of our planet. Planets B and C orbit their parent star in the periods of 1.51 and 2.42 days respectively. Initially, according to astrophysicists, both of these planets were comparable to Venus in all but exceptionally high temperatures. However, after their mass and density had been measured, it was TRAPPIST-1 that could be called Venus's analog. TRAPPIST-1b, the second closest planet to its star, is likely to contain a large amount of water and other volatile elements. The new data enabled scientists to find out more about the other discovered planets too. It takes TRAPPIST-1d 4.05 days to orbit its star. Its radius is 0.77 that of the Earth. The orbital period of TRAPPIST-1e is 6.1 days. Its radius is 0.92 that of the Earth. The orbital period of TRAPPIST-1f may last up to 9.2 Earth days. Its radius is 1.04 that of the Earth. The orbital period of TRAPPIST-1g is 12.3 days, and its radius is 1.13 that of the Earth. Last but not least, TRAPPIST-1h is the 7th object and is the furthest from its star, with a rotation period of 18 days and a radius of 0.7 that of our planet. It should be mentioned that the initial estimates of the object's masses were likely to be rather conservative. Due to the analysis of the density of the first 6 planets, it was later ascertained that they contain a big amount of water and other volatile elements, which makes them considerably lighter than thought previously. As for the furthest of them, E, F, G, and H, for all we know, they may consist entirely of water. Only TRAPPIST-1c boasts a mass bigger than initially estimated, which may be indicative of over 50% of iron in its composition. Of the 7 planets known to be located in the TRAPPIST-1 system, 3 of them find themselves within the habitable zone, namely D, E, and F. Speaking about the rest of them, following the estimates of its density, planet B is thought to contain either a small nucleus or else a considerable amount of volatile elements. Due to high temperatures of 127 and 69 degrees Celsius above zero on the surfaces of planets B and C respectively, water is not likely to remain in its liquid state there and is bound to float about as vapor. As for planets G and H, they are too remote from their central star to be potentially habitable. However, according to models suggested at Cornell University, the habitable zone of TRAPPIST-1 may well be wider, and allowing for volcanic hydrogen potentially acting as a greenhouse gas, there may be 4 planets within the habitable zone rather than 3. The density of TRAPPIST-1f is rather low too, and so it may well turn out to be an all-ocean planet. Here are the temperatures for all the planets in the system. The steady-state temperatures are given without including incident light dispersion and greenhouse effects. Just to compare, the steady-state temperature on our planet in the same conditions would measure 4 degrees above zero, and on Mars 47 degrees below zero. In November 2017, it was posited that the activity of the star didn't allow its planets to form and maintain their own atmosphere. It is accounted for by the fact that TRAPPIST-1 goes through periods of active flares, which may negatively affect the nearby celestial bodies, and thus render them uninhabitable for living organisms as we know them. Interestingly, the planets are located much closer to each other in comparison to our system's planets. The planet Mercury, which is the closest one to the Sun, is located 0.39 astronomical units from it, while the distance between TRAPPIST-1b and its parent star is just 0.01 astronomical units. As TRAPPIST-1 is a rather dim star, it is no easy matter to explore it. Red dwarfs like that are quite widespread across the universe, accounting for most of the galaxy's stellar matter. Plasma ejections on these stars are a rare occasion, although astronomers believe that there may be giant cold areas and compact hot areas with temperatures upwards of 4000 kelvins on the surface of TRAPPIST-1. If this conjecture proves to be true, scientists will proceed to confirm that the system's planets are constantly bombarded by powerful ultraviolet and X-ray radiation, which is able to destroy their atmospheres and render their surface completely sterile. The reason for that lies in the fact that none of the microorganisms known on the Earth are able to withstand intensive radiation emanating from flares of this kind, including the most radiation-resistant bacteria Deinococcus radiodurans. Nevertheless, in December 2017, atmosphere was proven to persist even in periods of high activity of stars, which implies that planets G and H may potentially have their own atmospheres. At the moment, astrophysicists' idea is to use more up-to-date telescopes for studying the matter. For example, the James Webb Space Telescope, whose launch is planned for March 2021. Today, the TRAPPIST system presents a great interest for the global scientific community, and even though it is highly unlikely that any advanced civilization will be discovered on its planets, we cannot ignore the fact that life forms in the universe may be extremely diverse and may differ from our perceptions of life as we know it, which implies that not all intelligent organisms are supposed to follow the scenario of our planet. If science manages to find out more details about this system in the nearest decades, many conjectures and doubts we have today about TRAPPIST-1 will most likely be cleared. Mankind has come across some extremely powerful radiation that reached us from deep space several times in the last 50 years. But as often is the case with space discoveries, the source was slow in being detected by astrophysicists. 1979. 3 US Vela satellites monitoring nuclear tests on the Earth detected an unusual gamma-ray flare. 1992, astrophysicists assumed that there was a celestial object out there not known to science with a huge electromagnetic radiation coefficient. 1998, a gamma-ray flare in the constellation Aquila. A number of measuring devices registered an unaccountable anomaly with its source located tens of thousands of light-years away from us. 2004, all telescopes in the world were for a short time dazzled. Less than a second later, every cubic centimeter in the solar system experienced a wave of gamma-ray radiation, the most massive burst in the entire history of observations. And today we're closer than ever to finally putting our finger on the nature of this discovery. A magnetar is a neutron star with an exceptionally powerful magnetic field of about 10 to the power of 13 teslas, which in essence is trillions of times that of the electromagnetic radiation on the Earth. It is also one of the rarest and really most dangerous phenomena ever encountered by mankind. When a supermassive star is on the point of dying, a supernova occurs. Among the multiple scenarios of what may take place after that, only one may lead to the star becoming a magnetar after the supernova. Many of you would have heard about the Russian roulette at least once in your lives. According to the rules, only one cartridge is put in the revolver's cylinder. The chance of producing a shot after you have spun the cylinder is rather small. However, when it does happen, the consequences are truly mind-blowing. Be it as it may, scientists are still at odds over what exactly this scenario would look like. According to the first theory, it's the inner energy of the star and its rotational energy that influence the formation of a magnetar. If a neutron star is formed at the time of fast rotation, the inner energy of this star as well as its rotational energy, which is of great significance in the first several seconds, all create a powerful magnetic field. This process is known to science as a dynamo mechanism. But there is another theory as well. After the accretion process, the magnetar may be able to receive energy from another star. Scientists have discovered a magnetar which is on an escape trajectory from our galaxy. Most moving stars we know set off on their trajectories as a result of supernovae in binary systems. This means that the accretion process takes place between the two stars with a common mass center in a binary system. Matter from one star gradually flows to the other. In this case, this is the source of energy for a potential magnetar. Something similar happens with a basketball spinning around the edge of the basket. Sooner or later it is going to fall, but it's the spinning process that predefines the direction of the fall. Magnetars spin on their axes extremely fast, with a speed varying between tens and thousands of times per second. At the same time, their dimensions are record small. As a rule, the diameter of a magnetar reaches a measly 20 to 30 kilometers. Just to compare, the diameter of the Moon equals 3,474 kilometers. That is about 173 times that of the average magnetar. The mass, however, is a completely different matter. A magnetar with a diameter of 15 kilometers will be significantly heavier than our Sun, despite the dimensions. It is its staggeringly powerful density of the interior that is the reason for its high magnetic radiation. For instance, 1E1048.1-5937 is an anomalous X-ray pulsar located 9,000 light-years away in the constellation Carina. The star the magnetar evolved from had the mass 30 to 40 times that of our Sun. The matter in these stars is dense to such a point that a fountain pen cap would weigh billions of tons, and a human would be torn to bits within a matter of seconds after landing on the star's surface. Several years ago, astronomers from NASA managed to register a phenomenon which came to be known as a starquake. Thanks to the Fermi Gamma-Ray Space Telescope, scientists received data about intense X-ray bursts. Their source was magnetar SGR J1550-5418. The magnetic field of this star is so powerful that from time to time its crust bursts with vast amounts of energy released through the crack. Such starquakes are the source of pulsed electric current. In theory, if a magnetar of this kind at its most active were to find itself within the boundaries of the solar system, we wouldn't as much as notice the threat, as the ozone layer of the Earth, together with all organic life forms, would be wiped off within a matter of a few hundredths of a second. Fortunately, however, the magnetar closest to us is a safe enough distance away. A magnetar is hard to approach not only due to the gravitational properties of its core and energy flares at the time of a starquake. When a magnetar is in its stable condition, its magnetic field is able to mess with electric devices hundreds of thousands of kilometers away, and within the radius of 1,000 kilometers, any object would be reduced to atoms. In order to systematize the difference in their radiation, scientists decided to divide magnetars into two varieties by using abbreviations. Rather than the full names, you will see these in any astronomical catalog. SGR, soft gamma repeater, and DXP, anomalous X-ray pulsar. In essence, SGR and DXP are different phases in the life of one and the same object. According to scientists, a magnetar exists as an SGR pulsar for the first 10,000 years. That is, it's a pulsar visible in regular light and repeatedly emitting bursts of soft gamma rays. As time goes by, it exhausts its properties and recedes into the invisible spectrum, when it can be seen to us only in the X-ray range, as an AXP. According to different sources, today among billions of neutron stars, the number of known potential magnetars ranges from 30 to 150. There are about 12 of them in the Milky Way. The magnetar is a soft gamma repeater, and if a starquake were to take place on its surface, it would affect us only by some slight changes in the top layers of the ionosphere. Due to their small dimensions and remoteness relative to the Earth, magnetars cannot be observed through regular amateur telescopes. The method of infrared or X-ray scanning of the sky is usually employed to observe them. Nevertheless, thanks to their active magnetic field emission and radiation, these stars are much easier to detect with the use of various instruments. This is exactly what took place several years ago, in 2013. Astronomers claimed to have discovered a magnetar in close proximity to a supermassive black hole right in the middle of the Milky Way. The star was detected thanks to several orbital telescopes, including the Chandra X-ray Space Observatory. SGR 1745-2900 is only 0.3 light-years away from the edge of the black hole, and to date it remains the only neutron star to have been discovered in close proximity to an object of this scale. SGR 1745-2900 has been observed by scientists ever since its discovery. Several years ago, the level of its X-ray radiation was proclaimed to be significantly lower than that of the stars of this category. The news prompted numerous debates. Can these changes have been caused by the black hole in the star's environs? After 2 years of observing SGR 1745-2900, astrophysicists came to the conclusion that, all things considered, the distance of 0.3 light-years is insufficient for any interaction in the magnetic or gravitational field to take place between the black hole and the magnetar after all. The reason is likely to lurk elsewhere. A magnetar's lifespan is quite short, just about 1 million years, and it's quite natural for its magnetic field to gradually die down throughout the star's existence. Some scientists assume that these processes may be the reason for the change of the star's status. In this case, magnetars can switch their category, flare up more frequently or less often, deplete the stock of the matter, and thus go from the category of SGR to the category of AXP. In its autumn years, a former magnetar that managed to survive the dissipation of its magnetic field may even become quite a different kind of star, namely a thermally emitting neutron star. So far, just about 7 objects of the kind are known to science. For their number, this group has been dubbed the Magnificent Seven, and each of them may once have been one of the most dangerous objects of deep space. But in order to establish that, it will take us long years, further technological advancements, and dedicated people willing to devote their lives to searching for solutions to the most dangerous and incredible mysteries of the universe. A perfect example of these eerie celestial objects are black holes. Their sheer existence was considered impossible until only recently, when on the 10th of April 2019, the National Science Foundation in the USA showed the world an image revealing a black hole in the middle of the Messier 87 galaxy. This object has a mass approximately 6.6 billion times that of the Sun, with a diameter of about 100 billion kilometers. Just to compare, the diameter of the Earth is only 12,742 kilometers. This hole falls into the category of supermassive black holes. A similar object can also be found in the center of the Milky Way. It is called Sagittarius A and boasts from 2 to 5 million times the Sun's mass, according to different estimates. The diameter of Sagittarius A is 45 astronomical units. In other words, 45 times the distance from the Earth to the Sun. But is it possible to admit of the existence of even larger black holes in space? And which of them is the largest? Let's figure it out. A black hole is a term referring to an area in space with an incredibly powerful gravitation in the center. As a rule, these objects are rather small at first and are able to expand as they actively build up their masses. Black holes are categorized according to their masses. The heavier ones are called supermassive black holes. At the moment, scientists haven't formed a unanimous opinion as to how these objects come about in space. According to the most popular theory, that of gradual expansion, when a black hole appears, it has a mass typical of a star, and later on it grows by sucking in the surrounding matter. The amount of information accumulated by science about these objects is rather scarce, but even based on the current data, a supposition can easily be made about there being at least several such holes in the center of any large galaxy. In the time the universe has existed, a few million or even billion of black holes are likely to have been formed in it by now. At least today, only a small fraction of them is known to us. The champion in terms of its mass is the black hole in the center of a quasar known as Ton 618. This object was stumbled upon in 1957 when white dwarfs were being explored and initially caused a lot of puzzlement on the part of the scientists. The notion of quasars was to appear only 6 years later. That is why the nature of the object was rather vague. On photographic plates taken with a 0.7-meter Schmidt telescope, it was listed as number 618 and described as decidedly violet. It was only in 1970 that radio emission from Ton 618 was discovered at the Institute for Radio Astronomy of Bologna. This emission was indicative of the fact that it was a quasar, and moreover, the most luminous quasar known to science at the time. It is assumed that there's an accretion disk of hot gas in Ton 618 surrounding a gargantuan black hole in the center of the galaxy. The gas must move around the disk at a tremendous speed, reaching 7,000 kilometers per second. This object is located in the constellation of hunting dogs, or Canis Venatici, and is 10.37 billion light-years away from us. The galaxy containing Ton 618 cannot be seen from the Earth due to the luminosity of the quasar itself, which is 140 trillion times as intense as that of the Sun. The contemporary view on quasars defines them as active nuclei of galaxies at the first stage of their formation. The nuclei's supermassive black hole sucks in the surrounding matter, thus forming an accretion disk. This disk is the source of luminosity of enormous power that is sometimes more intense than the aggregate luminosity of all stars and galaxies like ours. The brightest quasar, which was discovered in January 2019, has the luminosity of about 600 trillion suns and is 12.8 billion light-years away from the Earth. What could be the mass of an object finding itself in the center of a light cannon like this? According to today's estimates, the mass of the black hole in the center of the Ton 618 quasar reaches 66 billion times the Sun's mass, which makes it the heaviest black hole in our galaxy known to science. Black holes of this mass are categorized in a different group and are referred to as ultra-massive black holes. In fact, the Ton 618 quasar isn't the only object in this category. Within the constellation of Cancer, for example, which is 3.5 billion light-years away from us, the OJ287 quasar is to be found. It has a black hole in the center and is 18 billion suns masses. In the center of the Phoenix cluster, there's a rapidly expanding black hole, which at this moment is 20 billion times the sun's mass, building up 60 suns masses a year. One of the best-known black hole giants is located in the galaxy NGC 1277 within the Perseus constellation. The object reaches 21 billion suns masses, and its event horizon diameter equals 130 billion kilometers, which is 15 times the distance from Neptune to the Sun. However, at the moment, this giant practically isn't being active. Speaking about size, the undisputed holder of the first place on the list is admittedly another well-known space object, namely the black hole in the center of Holmberg 15A, a supermassive elliptical galaxy located in the constellation Cetus, or the Whale, 700 million light-years away from the Earth. This black hole isn't a champion in terms of its mass, which is 40 billion times the Sun's mass. Its dimensions, however, can't but amaze. According to today's estimates, the event horizon of this black hole could be as big as to accommodate our Sun and all of its planets. Its diameter is approximately 790 astronomical units. The Holmberg 15A galaxy must have been formed as a result of the collision of two smaller galaxies at some point in the distant past. A similar process is likely to be expected in our system as well, when the Milky Way collides with the Andromeda galaxy in 4 billion years' time. For now, astronomers plan to continue studying the phenomenon of the black hole in Holmberg 15A by carrying out complex and detailed modeling. Scientists are going to collate the results of theoretical calculations with practical observations in the future in order to try to establish how exactly it was possible for a tremendous black hole to come into being inside the two galaxies on their collision. In comparison to the objects mentioned above, our own planet may seem of no significance at all on the overall space map. But it should be noted that the age of practically all the supermassive objects in the universe is several times that of our Earth. For millions of years, these black holes have been gaining in their masses and expanding as the time went by. Today, we can observe their activeness as the result of the development of the entire universe. It is quite feasible that most of the ultramassive black holes were formed as a result of smaller holes merging. A similar process takes place when they collide, which is accompanied by the emission of gravitational waves. These occurrences must be the biggest contributors to the generating gravitational waves in the universe and are exceptionally attractive to scholars of gravitational wave astronomy. By now, several similar signals which came about as a result of two small black holes merging have been registered by the American observatory LIGO. Perhaps we will find out the names of other champions in the list of space giants in the near future. And now, all we have left to do is just await new, amazing discoveries. We live on a planet that is considered young in comparison to other planetary objects. Humanity is just 2.8 million years old, while the Earth is 4.5 billion years old. Long before our planet appeared, thousands of such habitable worlds were already in existence, and these objects are still somewhere in the nearest galaxies. Imagine if mankind had appeared a billion years earlier. What technologies would we have had at our disposal today? based on calculations by a number of today's astrophysicists, it is an undeniable fact that there exist a great number of similar planets in the space. The presence of an advanced extraterrestrial life on such planets is simply a natural consequence. Why is it then that we still haven't received a single sign that would indicate the presence of anyone else around us in the space? What could be the reasons for this absolute silence of the universe? To try to answer this question, I will tell you about one of the most atypical and fascinating puzzles of modern cosmology, the Fermi paradox. Enrico Fermi is a scientist of Italian descent who emigrated to the United States shortly before the outbreak of World War II. Fermi worked on the design of the first nuclear reactor, but he became well known for a phrase he happened to drop in the cafeteria of the Los Alamos laboratory. During an informal conversation in 1950, Fermi, together with 3 other colleagues, were discussing a cartoon published in the New Yorker magazine. There was a picture of aliens unloading trash cans from flying saucers landed on their planet. The cartoon was associated with real disappearance of trash cans in New York, and aliens got into the picture because of the growing interest in extraterrestrial civilizations in those years. When discussing this cartoon, the scientists grew to be more serious, and then Fermi uttered a phrase that was to lie in the basis of an entire paradox. Have you ever wondered where they are? According to the scientist's idea, if extraterrestrial civilizations could really exist, we would have had at least 3 types of evidence: the presence of alien probes, ships, or radio emissions. However, despite all the ongoing research, none of these has been discovered so far. But Fermi was by far not the only scientist who thought about this. This question was raised much earlier by the Russian philosopher and inventor Konstantin Tsiolkovsky, and in 1975, astrophysicist Michael Hart described in detail the reasons of this paradox. Fermi's question was a sensible one to ask. Just imagine, any one of us can look at the night sky right now and see thousands of small stars. According to scientists, there are about 100 billion of them in the Milky Way alone, 20% of which have their own planetary system. Furthermore, in each of these systems there should be at least one planet similar to the Earth, and 10% of these planets that can potentially support life may well have an intelligent civilization. How is it possible that with such a high probability of the existence of extraterrestrial life, to solve this riddle, the American astronomer Frank Drake developed a simple mathematical formula in 1961. It calculated the probability of existence of intelligent races in the universe. Here is this formula. N. This is the number of civilizations which use communication methods that we could detect. I is the average annual rate of emergence of stellar systems in our galaxy. F sub p is stars that have planets. N sub e is the number of planets or satellites that can potentially support life. F sub l is the number of inhabited planets that develop life. F sub I is the probability of the emergence of intelligent life on inhabited planets. F sub c is the fraction of civilizations with detectable forms of communication. L is the time length of a detectable signal. Many astrophysicists have tried to calculate each of the presented values, but to this day, the Drake equation has no final solution. Given the absence of any signals from nearby stellar systems, it can be assumed that any civilization that grows to be technologically advanced runs a great risk of inevitable self-destruction. For example, due to a nuclear war or ecological collapse. Thus, any developed race has very little time to be noticed. However, if this does not happen, any civilization will sooner or later reach a level of advancement that is thousands of times higher than ours. In 1964, Soviet astrophysicist Nikolai Kardashev developed and published the method of technological advancement of civilization called the Kardashev scale. Using this method, the scientists suggested an idea about the capabilities of such developed races. These capabilities would depend on the amount of useful energy they could make use of. According to Kardashev, the first type includes civilizations that are able to use all the energy available on their planet. More developed races can use all the energy emitted by the main star. And the third type of race is able to use the energy of the... According to astronomer Carl Sagan, so far our level is 70% that of civilizations of the first type, and we will be able to reach their level completely in 1 or 2 centuries. But even earlier organisms that appeared in the universe comparatively recently could well have reached the level of advancement of the third type of civilization. With this kind of technologies, any races will be able to move through the space at a speed close to the speed of light or even faster. If this really happened, we would hardly miss signs of their presence. However, the universe has never given us a single sign of this. It is likely that the reason for this is that we use only radio observation methods to search for other civilizations in the galaxy. In the entire history of the research on extraterrestrial civilizations, not a single star has been discovered that would demonstrate unusually intense radio waves. This leads us to the conclusion that we're the only civilization in our part of the galaxy that uses radio waves for communication. Perhaps if other civilizations do exist, we don't notice them because they use completely different types of communication. The universe is full of things we're unaware of, and if someone does live thousands of light years away from us, they might be able to use channels of communication unknown to us, for example neutrinos. Unfortunately, this version of the solution of the Fermi paradox is not the only one. Many scientists believe that our solitariness in the space is an inevitable fact. Maybe we simply don't know why other civilizations have died out. Others suggest that we simply have not yet reached the level of development sufficient for communicating with the universe, so it keeps silent. Others, proponents of the so-called zoo theory, believe that our level of development is too low compared to extraterrestrial races. Our radio signals disappear into the distant depths of the outer space without a trace. And who knows, maybe those who see them simply don't understand what they mean. Or maybe intelligent aliens are aware of our attempts, but will respond only in the fullness of time. While traveling around the universe, we have taken a look at only a few phenomena and space objects. Had we continued our journey, we would quite literally never have seen the end of it. The variety of as yet unexplored celestial objects and phenomena defies human understanding, and the lifetime of every human on Earth would not be enough to even talk about them all. But this is anything but a reason to give up on our search. And the process of studying and exploring the universe will continue as long as the human race exists in its tiny, habitable portion.